We are going to do applied optimization problems in this video. So, what are optimization problems? Well, they're real world problems where we're trying to maximize or minimize something. So, in number one here, we're going to try to maximize the area of a certain field. And two, we're trying to maximize the profit. So, in this video, we're actually going to look at problems one, two, and three. Three has to do with a deli that's trying to find the optimum price to price its sandwiches at in order to maximize its revenue. And I'll also give you an idea of how to do number four. So we won't actually do number four, but number four is similar to number three, and I'll give you an idea of how to do that. Now, in the next video, we'll look at problems five and six. Now, problems five and six are different than problems one through four because they don't deal with quadratic functions, they deal with different kinds of functions. So, number one says a rectangular field is to be bounded by a fence on three sides and by a straight stream or a river on the fourth side. Find the dimensions of the field with maximum area that can be enclosed using 1,000 feet of fence. So, I've drawn a picture here. So, the blue here represents the river or the stream, and we're trying to enclose this rectangular field using fencing. We have 1,000 feet of fencing. So, the fencing here is in red. So, let's go to Desmos. Now I've drawn this diagram in Desmos with some sample dimensions here. So suppose we use 200 feet of fencing right here and 200 feet of fencing right here. Well, how much fencing are we left with for the top part here? Well, 600, right? It has to add up to 1,000, right? We have 1,000 feet of fencing. So notice how much area have we actually enclosed? Well, this is a rectangle with length 600 and width 200. And 600 times 200 is 120,000. So we've enclosed 120,000 square feet. Now, is this the best way to do it though? Well, we could change the dimensions a bit. So let's change this so that this length is 100 and this length would be 100. Then what we're left with on the top is 800. Well, here we've only enclosed 80,000 square feet. So we've kind of gone in the wrong direction. We've enclosed a smaller area. But maybe we can change the dimensions so we actually enclose a bigger area. And in fact, we can. Now, what are the optimum dimensions, though, that will give us the maximal area? Well, one thing that we can say for sure is we don't want to have it too narrow down here. In fact, we could have the width be zero. If we went up 500 and then down 500, we go across zero. Well, that would be a terrible strategy, right? We've enclosed zero area. Likewise, if we go the exact opposite direction here and use up all 1,000 feet of our fencing here and go down zero and down zero, well, again, we've enclosed 0 square feet. So there's got to be a happy medium in here somewhere. Now, you might be tempted to say, well, maybe it's when it's a perfect square. Okay, when it's 333 and a third by 333 and a third, but it turns out that's not going to be what produces the largest possible area. In fact, what we're going to want is for this top side to be a little bit longer than these two sides. Now, why would that be the case? Well, because we don't need any fencing over here. And since we're not using fencing over here, it's going to be more optimal to have a longer top side than these sides over here. So let's figure this out. Well, this length of fencing here, let's call this length here X. And if that's X, well, then this side over here will also be X. Now, what is this side length here? Now, you could call it Y or something, but actually, let's not call it a new variable. Let's think about what this is. Well, if this is X and this is X, we've used up 2X amount of fencing for these sides. How much fencing are we left with? Well, if we have 1,000 feet total of fencing to use, what we're left with is 1,000 minus 2X here. So imagine, for example, X is 100, right? So if X was 100, this side would be 100. What would this length be? Well, it'd be 1,000 minus 200. It would be 800. Now, what is the area? Well, the area of a rectangle is length times width, but our length is 1,000 minus 2x, and our width is x. So this is our area. In fact, we could call it A of x. A of x is 1,000 minus 2x times x. Now, we can actually distribute the x here and write this as 1,000x minus 2x squared. Now, one other thing I want to point out is that x can't be just anything. In fact, x has to be greater than or equal to 0, and also x can't be bigger than 500. Because if x is 500, if we go up 500 and up 500 here, well, we have 0 to go over. So the x, the amount of fencing we're using on this side, has to be somewhere between 0 and 500. So what we're trying to do is to maximize a of x, maximize the area when x is between 0 and 500. So how do we find the maximum of a of x? Well, we need to find the critical numbers. What is a prime of x? Well, a prime of x is going to be 1,000 minus 4x. And then if we factor out a 4, we can write that it says 4 times 250 minus x. So what are the critical numbers? What number, what value for x makes this be 0? Well, either looking at this expression or this expression, I think you can see that it's x equals 250 that is going to be our critical number. Now, to determine if that x value actually makes the a of x be maximum, we're really maximizing a of x, we should also check the endpoints. But actually, a of 0, you can check here with the formula for a. If you plug in 0 for x, whether you use this formula or this formula, if you plug in 0 for x, it's going to be 0, right? If we go up 0 and up 0 here, so we're over 1,000, we even close 0 area. Same thing, a of 500. Okay, if we use that, also that terrible strategy of going up 500 over 0 and down 500 again, well, you can see if you plug in 500 for x, plug in 500 for x here and here, that's going to be 0. So actually, it's going to be at 250 that a of x is a maximum. Well, what is the maximum? Well, what is a of 250? Well, we could plug it in either here or here. I think it's probably easier to plug it in here. In fact, what we get if we plug in 250, 2 times 250 is 500. 1,000 minus 500 is 500. And plug in 250 there, we have 500 times 250, and that's 125,000. So that's 125,000 square feet. That's the maximal area that we can enclose. Now, what are the dimensions? Okay, what is the length and what is the width? Well, the width here is going to be this x, right? The x is the 250. And what's left up here, that'll be the 500. Okay, when x is 250, this is 250, this will be 500. And when we make a rectangle that way, that'll give us the largest possible area. The area is 125,000 square feet. And in fact, looking in Desmos here, we see when it's 250 and this is 250, this would be 500. It's 125,000 square feet. If I were to make this length just a little bit bigger or a little bit smaller, the area is going to go down. So let me make it a tiny bit bigger. Notice the area went down. Or now if I make it a little less than 250, it also goes down, right? The area went down. So to maximize the area, our dimensions are 250 by 500. Okay, let's do number 2. Suppose the revenue and cost in dollars of producing and selling X units. Now, I'm not saying what the units are, so maybe this is like X candy bars or X cell phones, whatever it is, are given by these formulas. So we have a formula for the revenue and a formula for the cost. Find the maximum profit and the number of units that must be produced and sold in order to yield the maximum profit. So what is the maximum profit and what is the X value that gives you that maximum profit? Now let's remember that the profit is equal to the revenue minus the costs. And the revenue is given by this formula. And we're going to subtract the costs. Now, if I just write it like this is not correct. Remember, I'm subtracting the whole cost function. So I should put this in parentheses. So that negative is going to distribute. We're going to have a negative 7x and a negative 12. Now, if we simplify this, we get negative 1.5x squared. Now, notice we have a plus 82x and a minus 7x. So that's really plus 75x. And then we have a minus 12. So that's our profit function. Now we're trying to maximize the profit. So what value for x will allow this to be largest? And one thing I want to point out, this is actually a quadratic function, and notice it has a negative leading coefficient. If we were to graph this p of x, the graph is going to look like a parabola like this, where it's opening downward. So it actually will have a maximum, and that maximum is going to occur at a critical number, right? A place where the slope is 0. So let's find that critical number. Well, p prime of x is going to be, well, if we multiply 2 times 1.5, we get 3. This would be negative 3x plus 75. And let's factor out the negative 3. Write this as negative 3 times x minus 25. So notice, what's the critical number? Well, what value of x can we plug in here that will make the derivative be 0? What number can we plug in here to make this 0? Well, notice it's x equals 25. Now, what does this mean? Is this $25? No, 25 is the X value that's going to maximize the profit. Okay, now what is that maximum profit? Well, we have to find P of 25. Now, not P prime of 25. P prime of 25 is going to be 0, right? That's the slope there. It's going to be 0. What is P of 25? Well, we need to plug in 25 for X here. So we have minus 1.5 times 25 squared plus 75 times 25 minus 12. And when I did that, I got this. And maybe one of the hardest things about this problem is just making sure you plug things into a calculator correctly. And I ended up getting 925.5. So what does that mean? Well, the maximum profit is $925.50. And that occurs when 25 units are produced and sold. And in fact, looking in Desmos here, you see our profit function here, P of X graphed, and notice it's this parabola. And this point up here is 25 comma 925.5. So we maximize the profit when 25 units are produced and sold. And the profit itself is $925.50. Okay, to finish off, let's look at number three. A deli sells 800 sandwiches per day at a price of $9 each. So notice the revenue there would be $7,200, right? So 800 sandwiches at $9 each, they'd make $7,200 in revenue. A market survey shows that for every 15-cent reduction in the price, 20 more sandwiches will be sold. So if they reduce that price by 15 cents, so let's say $8.85, then they would sell 20 more sandwiches. They would sell 820. Or if they reduced it by another 15, so reducing it by a total of 30 cents, so the price being $8.70, they would sell 840 sandwiches. So the question is, how much should the deli charge per sandwich in order to maximize the revenue? And we're going to assume that the deli does not want to increase their price. So we're only looking at price decreases. Now, notice that the revenue generated is going to be the price per sandwich multiplied by the demand for sandwiches. So when the price was $9, the demand is 800 sandwiches, and the revenue will be, well, 9 times 800 is 7,200. Now, if the price decreases by, say, 15 cents, so the price is now $8.85, then the demand will be 820 sandwiches. And if you do that on a calculator, it turns out that you get $7,257. So notice the revenue actually went up by decreasing the price. There was no guarantee that that was going to happen. It just turns out that it happens in this problem. Now, the thing is, you can't keep decreasing the price forever and expect the revenue to keep increasing. So if you decrease it all the way down to zero, let's say, well, no, even if the demand is really huge at a price of zero, you're still going to generate zero in revenue. Okay, so how much do we want to reduce the price in order to maximize the revenue? Now, we're going to define a variable. We're going to let X be the number of 15-cent price reductions. So if X is, say, 2, then that means we have two 15-cent price reductions. That means we're decreasing the price by 30 cents. Now, notice then that the price will be 9 or $9 minus 0.15 times X. So again, if X was 2, this would be 0.30, and 9 minus 0.30 would be 870. That would be the price. Or if we have 10 price reductions, that means we're decreasing it by $1.50. Well, then the price would be 9 minus $1.50. That'd be 750. Now, what about the demand? Well, the demand is going to be 800 plus 20 times the number of price reductions. So if the number of 15-cent price reductions is 1, then this will be 820. If the number of price reductions is 2, this will be 840, and so on. And let's remember that the revenue will be the price times the demand. So let's actually write this out. The price will be 9 minus 0.15x, and the demand is 800 plus 20x. And this is the revenue. We'll call this R, or really R of X. Now, one thing I want to point out here is that in the previous example, we looked at an R of X. There, it was also dealing with revenue, but the X was not the number of price reductions in that case. The X was the number of units produced and sold. So here our X means something different than the previous problem. Here, our X is the number of 15-cent price reductions. Now, one other thing I want to point out is that our number of price reductions is between 0 and 60. Now, why is it at least 0? Well, if we go back to our problem, assume that the deli does not want to increase the price. So we don't want to have a negative price reductions, in other words, a price increase. So we want our X to be greater than or equal to 0. And also, X can't be greater than 60 because if you do 60 price reductions of 15 cents, that will be $9 of price reductions. And if you reduce 9 by 9, you get to 0. So how did I actually get 60? Well, what you could do is you say you want 9 minus 0.15x to be greater than or equal to 0. If you solve that for x, then you can see that x has to be less than or equal to 60, right? 60 price reductions would make 9 minus 0.15x actually equal to 0. So the question is, what value of x is going to maximize the revenue? Well, it's either going to occur at one of these endpoints. Now, it's not going to occur at 60 because with 60 price reductions, our revenue is going to be 0. It could be that we don't want to reduce it at all. Okay, we do want to have 0 price reductions, and that would maximize the revenue. Although I think we just showed right here that 0 is not going to be the best option because we reduced it one time here and we already increased the revenue. So to maximize our revenue, we're going to want to find the critical number or critical numbers of this function. So we need to find r prime of x. Well, before we can find r prime of x, let's FOIL this out. If we multiply 0.15x times 20x, 0.15 times 20 is 3. So this is going to give us a minus 3x squared. That's multiplying these two terms. If we multiply 20x times 9, that's going to be 180x. And if we multiply 800 times 0.15x, well, 800 times 0.15 turns out that it's 120. So this would be minus 120x. And last of all, if we multiply 9 times 800, that's 7,200. Okay, and if we simplify this, we get minus 3x squared. 180x minus 120x is 60x plus 7,200. Okay, so what did I do here? Well, we found our revenue function by doing the price times the demand, and we found the price and the demand by these equations. Then we FOILed this out and simplified it down. Now what we need to do is take the derivative. Okay, r prime of x is negative 6x. Oh, I forgot to put the x there. Plus 60. So what are the critical numbers? Well, let's pull out the minus 6. Write this as minus 6 times x minus 10. And notice that we have one critical number, and that's x equals 10. Okay, so what's the revenue generated when we do 10 price reductions? Well, you could plug in 10 for x here, or you could just kind of think about it. What's really happening? Well, with 10 price reductions of 15 cents each, notice what is the new price going to be? Well, we're reducing it by $1.50. So 9 minus $1.50 is going to be $7.50. It's going to be $7.50 times, well, with 10 price reductions, it's the demand is going to go up by 200, right? So the demand will be 800 plus 200 is 1,000. So $7.50 times 1,000 will be 7,500. That will be the revenue when we do 10 price reductions. Now, remember when we did no price reductions, remember it was 9 times 800. $9 was the price, 800 was the demand. In fact, you can see that up here. If you plug in 0 for x there, you get 9. If you plug in 0 for x there, you get 800. If we multiply that out, we get 7,200. And if we look at the right endpoint, so we're looking at the endpoints here, we have 0 to 60. So r of 0 was 7,200. R of 60 turns out that it's 0. And the reason it's 0 is because if you plug in 60 for x right there, that becomes 0. The price is 0. And it doesn't even matter what this is over here. It doesn't matter what the demand is. If the price is 0, the revenue is going to be 0. So notice, what is our highest value of these three? Well, the highest one is this one. Okay, so the biggest revenue is generated when we do 10 price reductions of 15 cents each. Now let's look at what the question was asking. How much should the deli charge in order to maximize revenue? Well, we want 10 price reductions of 15 cents. So we want it to go down by $1.50. So that $9 is going to be reduced to $7.50. So the deli should charge $7.50 per sandwich in order to maximize their revenue. Now, you could also look at the revenue function here on Desmos and notice the x-axis is the number of price reductions. So notice when you have 60 price reductions, the revenue ends up being 0. But when you have 10 price reductions, that's when we're maximizing the revenue. The revenue is then 7,500. If you do 0 price reductions, so if you just keep it at $9 per sandwich, then the revenue generated was 7,200. So notice that we maximize the revenue with 10 price reductions of 15 cents each. Now, another problem that's very similar to this that we're not actually going to do here, but I'm going to give you an idea of how to do it, is this number 4. A car rental agency rents 200 cars per day at a rate of $40 per day. For each $1 increase in rate, 5 fewer cars are rented. Okay, and at what rate, in other words, at what price per day, should cars be rented to produce the maximum revenue? And what is that maximum revenue? Well, you do this problem in the exact same way as you do number 3. So here you can let X be the number of $1 price increases. And you can use that same equation, revenue equals price times demand. and write a formula for the price and write a formula for the demand. Then take the derivative of the revenue function, find the critical numbers, and you do it the same way, really, as we did number three.